So I'd like to talk a little bit about ultrasound physics. Now, before you turn your computer monitor and head to something else, give me a chance, because it's actually kind of fascinating how all of this works. And it really does apply at the bedside. To start with, I'd like you to understand how ultrasound is generated. So I have a crudely drawn ultrasound probe here. And the probe is based on this thing right here. And this is a crystal. It's a synthetic type of crystal that has been heated to a high temperature so that it can attain what's called a piezoelectric effect. Now what that means is that when a charge is applied to this crystal, it vibrates and creates a sound wave. And the thickness of that crystal determines the frequency of the sound wave. So when we go to talk about frequency and its application to clinical ultrasound, you can know that the crystal within the different probes determines what that range of frequencies is. Now within the crystal there's also electrodes. There's the live electrode and then the ground electrode. And these generate that charge coming from the machine. And so when they're applied to the crystal, it starts to vibrate and again generates that sound wave, which then gets transmitted out of the front of the probe. Now, if you were just to apply that charge, the sound will go all directions from the crystal. So they also put in what's called a backing block in order to take those sound waves that are directed posteriorly and redirect them out the front of the probe. And so all of this is hooked up to your computer, i.e. the monitor that you're working with, and it sends out the signal and then receives it back to generate the images that we want to see on the computer screen. Now, there are several properties of sound that we need to talk about. So, the first of which is what's called propagation speed. So, propagation speed is really determined by the medium. So each medium will have the same propagation speed. So let's say we're sending two different frequencies into fat. So we'll say one is 5 megahertz down here, and the other one is 0.5 megahertz. And we're going to put them into some fat. And so when they go through the tissue, despite the fact that their frequency and wavelength are different, their speed through that given tissue is exactly the same. Conversely, if we take two different materials, so let's say muscle and bone, and now we're going to take the same 5 megahertz frequency in both cases. Because bone is stiffer and it is denser, the propagation speed will be much faster through that medium than through the muscle. So again, propagation speed is determined by the medium. Some other concepts that we need to understand are how sound interacts with the tissue itself. And there's a couple of different concepts that we should talk about. So the first is reflection, and then refraction, and this goes right along with the angle of incidence. And then impedance, and finally attenuation. So we'll take each of these one at a time. So reflection, I'm going to draw kind of a crude body here. And then we have our ultrasound probe up here. And we've got some tissue boundaries within it. So anytime there is a boundary with two different densities, that sound wave is going to get reflected back towards the transducer. And the transducer is going to recognize that, and it's going to run some calculations to figure out how deep that barrier is, and it's going to put up a picture on the screen. This is the major concept behind pulse echo systems. So impedance is that property that occurs between the boundary of tissue A and tissue B. So as long as there's a difference again in the density, which then makes for a difference in propagation speed, there will be waves that get reflected back. Now if there's weak impedance, so the tissues are pretty close to each other, most of the waves are actually going to pass through that boundary and only a few are going to go back. Whereas if there's a strong amount of impedance, such as bone or gallstones, you're going to get most of those sound waves reflected back towards the probe. So both bone and air have very high impedance. This is why we put all that gel, also known as coupling gel, against the bottom of the probe to minimize air so that we can get the sound waves into the tissue that we're looking at. It also explains why lung and bowel are a little bit more difficult to image than liver and kidney. Now, as far as refraction and angle of incidence, ultrasound assumes that you're going to hit the tissue at a right angle. Unfortunately, this isn't always the case. We know that the body has a lot of curves to it, and so sometimes that sound wave, instead of hitting it straight on, is actually going to hit it at an angle. And then the difference between the tissues is going to determine how that sound wave is bent in different directions versus how it's transmitted through. Likewise, because of the angle, some is going to get reflected back into space, and that will become important in a couple of the artifacts that we'll talk about in another lecture. So, again, this is an idealized situation where the ultrasound machine kind of thinks that everything's hitting the surface at a right angle, but really things are bouncing and bending. Now, fortunately, those rough surfaces really do help produce the images because the sound waves interact in so many unique ways that we get reasonably ideal images. Finally, attenuation. As that sound wave travels through the body, some of it is going to be attenuated by the body. And this really is a factor of the frequency. So it has to do with the frequency of the sound wave as well as the distance that the sound wave is traveling. So intensity is measured in decibels, and it's roughly change per centimeter of the decibel, and is greater the higher the frequency is. So a 3 megahertz probe, or a 3 megahertz signal, will attenuate by roughly 3 decibels in 1 centimeter, which is a loss of about 50%. 6 megahertz, however, will attenuate by 6 decibels in 1 centimeter, which actually is 75%. And as you can imagine, if you're going through a lot of tissue, so say you're imaging something that's 10 centimeters or 20 centimeters in depth, you're going to be attenuated by a factor greater than 1,000,000. So that's a lot of loss of power. This is why when we image structures that are deep, so a patient who's a little bit on the portly side, or a structure such as the aorta that's in the center of the body, we want to use a lower frequency probe. Now, the reverse of that has to do with resolution. So resolution is increased with frequency. So your higher frequency probe will actually give you better resolution than your low frequency probes, but you sacrifice your depth as a result of that. Finally, I wanted to talk a little bit about time gain compensation to finish up. So time gain compensation, or we'll just simply talk about gain, is how the machine actually takes those really deep signals and makes them easier to see. So as you send out a beam of ultrasound, and we're going to call this time down here. So your probe sends it out, generates a signal, and then the signal continues to propagate through the body, hits another structure here before it gets reflected back to the machine. Unfortunately, because of attenuation, this signal appears much weaker to the computer than the signal over here. So what the machine attempts to do over time is take that signal and then amplify it. So this is near field gain and this is far field, such that the returning image looks more like this. So that the intensity increases and you're better able to visualize those deeper structures. So essentially what the machine is doing is taking this far signal and amplifying it so that it's easier for you to be able to visualize it. So that's about all I have. Hopefully this is useful to you. And next time we'll talk about how to apply some of these factors to your ultrasound imaging at the bedside.